Hi there then, this is my battery built from 6 vape cells, part 2. I had a catastrophe, so I've put the cells into this heat-proof plastic and brought out the wires to the board here through a connector here, which then goes onto this connector here. I've still got my meters across the back to try and measure the voltage of the individual cells. I haven't solved the timing on these, so they do tend to flash and not be readable at times. And each cell connects on to this main it's not a battery management system board, it is just a protection board. A battery management system board would balance the cells so that if one cell was at 4.2 and one was at 3.5, it would average all the cells out so they were all at the same voltage. But this board can't do that. Can't say I'm upset, because I'd rather charge each cell individually to make sure that they're all at the right voltage, rather than trying one of these clever battery management systems. So where am I? Right, so I set it up and set it to discharge. When I did that, I took photos of it, set off then the actual circuit itself. What we have is the cells, the six meters here connected to each into an individual cell. The board here, which is green, has come out blue, presumably because of these blue LEDs for some reason. You can see here that this meter, which is intended for USB, but it seems to work with 24 volts reasonably well. And I've soldered the wires onto the bottom because it tended to overheat. I tried putting a heat sink on the end, but had catastrophe, so just soldered the wires on the bottom. As a load, I've got 4 car bulbs. These car bulbs are 12 volts, 21 watts. So what I've done is to arrange them as 2 in series, and put those in parallel. That way they drop 24 volts between them, which is the sort of voltage that I was looking for. And if you get 3.3 amps coming in, then presumably 1.65 amps go down this set and 1.65 amps go down this set. So they then act as the load for these cells that I'm using. At the start, I set it going. You can see the reading on the meter here. Took the photograph after I'd get it going, and it had done 15 milliamps by the time I started. Then after a minute I did it again and kept repeating this, taking photos at various times throughout the discharge. 11 minutes and so on, until finally, boom, it went off. The meter and the lights went off. So what had happened is, presumably one of the cells had got below the 2.7 volts that this chip is supposed to cut off at. I found that if I reconnected it very quickly, couldn't get my hand away in time, it had gone off before I could get my hand away. So when I did that, I found the reading here that after 21 minutes it was down to 18.7 volts. It had used 3.13 amps, and I had a total of 1100 milliamp hours. So it had come on but immediately go off again. I couldn't work out which of the cells was the problem, because these cells here, for example, are still at 3.3 volts. So it isn't one of those that's causing the problem. but of course I can't see with these that are the flash rate doesn't appear on the photo. So I suppose we could try that. The cells haven't been recharged since I did it, so let's see if we can recharge it and get some readings. It'll probably go off very quickly. Can I plug those in? Yes, it's on. Oh, it's staying on. I've got 3.3, 3.2, 3.19, 3.04, 3.3, 3.3 and 3.12. And it's gone off, and I missed which one actually went down to the 2.7. But of course now it's gone off. The cells have bounced back up again. Now they're not under any load. So yeah, that was what I did, and that was how I tested it. Obviously I wouldn't recommend this to anybody, not without the special using proper gear, proper voltage, sensing temperatures on it to check that nothing's overheating. This is purely an experiment to show that it can be done using one of these protection boards. So yeah, that seemed to work alright. It only worked up to, what was it I got? 21 minutes I got out of it at over 3 amps. Where are we? Let's have another look at this then. So the final sort of thing, if we go back to this, I got, after 21 minutes, I got the cells of 1144 milliamp hours. As I'd tested these cells at 100 milliamp discharge, not the 3 amp discharge, then I suppose that could be reasonable, because I got them at around 1400 milliamp hours. So that seems quite low, quite disappointing. I thought I might got more than the 21 minutes that I got. However, it did last for 21 minutes and give me that amount of amp hours. If we look at the voltage, at the graphs then that I did for this, oh, what's going on? Why are those lit? Oh, because I'm connected. If I disconnect, they should go out. They go out when I disconnect. So I'm measuring the voltages there on the cells, nothing to do with the battery protection mechanism. If I look at the graph, can I look at the graph that I've produced of the results I've got? I see a pretty straight line for the milliamp hours. This is time up here, and along the bottom here, milliamp hours in blue, and that seems to be a nice regular straight line with the times that I measured. And if we look at the current then, if we look at the current, which went from something like it's up at about 3.44 here, and gradually over time it reduces until after the 21 minutes it's down at 3.13 amps. So that is pretty much what I would expect from this system. But the big problem is the voltage. When I look at the voltage, yeah, cells are down 18.7 after the 21 minutes, and they seem to have a pretty smooth curve down to about the 11-minute mark. But before that, they're over here. They're off the scale. I didn't anticipate them being so far off. So they're over here somewhere until this point, when suddenly the voltage drops, and I suspect that I have a faulty cell in there, and that's what's done for this volts. It's suddenly given up the ghost, and that could be the problem, although I can't see it on the voltmeters. So what exactly happened, I have no idea. Anyway, so those are the results I got. I'm quite happy with those results as to where I've actually got with them. So if we have a look at this circuit board then again, let's have a look at our circuit board. Here it is in black and white. I'll follow the top down, that's just, where are we? There. That's just the bottom of the circuit board with its through holes, and then the areas of copper that relate to the various bits and pieces, with a few tracks underneath to connect bits together. It only seems to be a two-sided board. Don't seem to need anything more complicated than that. If we look at the actual layout of the board, then what can I see? Well, over here we have the inputs from the cells. So for example, B3 input goes in through this resistor here and then into one leg of the chip. Up here at the top we have a couple of resistors, drop-in resistors, so that the chip can actually know the current that's being used. Here we have two FETs which are used for the discharge, and here we have two FETs for the charge. The output here, P minus, then is different from B minus, but the output P plus is the same as B plus on the batteries. There's a diode across the outputs, presumably so if it's connected the wrong way round it blows the device that you put it onto. So what's this chip? If we have a look on the internet, all I can find is a Chinese data sheet, and it's very good because it shows us the circuit diagram, very similar to the layout diagram. Over here we've got the cell inputs, each goes through a resistor and then a capacitor down to the 0-volt rail, and they then go into the chip at this side. We have a couple of non-connected terminals, and the power is going in along this rail here, once again through a diode and a resistor. So that is more or less this right hand side. If we look at the left hand side, we have, what do we have? Down at the bottom we have the temperature sensor. This board hasn't got one fitted, they've just put a 10k resistor in place of the temperature sensor, and the power to the temperature sensor comes from this pin 4 up here. Down here we have the 0-volt rail which connects down here, interestingly. Is it 0-volt rail? No, that's not the 0-volt rail. The 0-volt rail is here, this one, which connects straight down. We then have what I assume these four go to what's called a battery gauge, a device that can measure the content of the battery, say how much percentage there is left, etc. But they're all just connected through capacitors down to the 0-volt rail. To the battery 0-volt rail, that's right. This is the 0-volts of the battery, which makes sense. Here we have our sense resistor, so that we have a couple of wires either side, one here going into VCS, and there must be, well, presumably it uses the 0-volt at this side to measure the difference between the two. Here we have our two FETs which are connected back to back so that the drains connect together, and then the sources connect either to the 0-volt here. So for the charge, then the current comes, then this is switched on and it lets the current go that way for the charging. It has a diode across it, and here we have the other FET connected the other way around with its diode. These diodes are important because when it's charging, this diode conducts, and when it's discharging, this diode conducts. So when the current's going from the batteries, this one, this one, I'm all confused, can't work it out. Anyway, it's something like that. These in turn then are switched on by wires from the this chip. So we have this wire coming down here, going to the gate. It has a resistor to pull the gate low when it's not being pulled high. So this pulls it high and that pulls it low. Same thing at this side, pulling them on and off. So that's my chip. This one happens to be, can we see it here, the can't read that, HTL 6036 AAA. And if we look at the figures for it, what we've got is V over charge or over protect, then is 4.25 volts. So if, for example, we are charging and one of the cells, and it only needs one of them, gets above 4.25, then it will shut off charging to all the cells, so that all the cells won't be fully charged. Some will be undercharged. And once it's cut off, then it won't come back on again and start charging again until the voltage has dropped to 4.1 volts. So it won't sort of cycle very quickly, one would assume. It would have to wait till one of the cells has dropped, the charged cell, fully charged cell, had dropped to 4.1 volts. Similarly with discharging then, when it's discharging, it should go down to 2.7 volts. So one of my cells must be really poor in terms of discharging, because I couldn't tell which one it was that got anywhere near 2.7. They seem to be at 3 volts, 3.3 volts when it shut off. And for it to come back on again, then the cell that's dropped down to 2.7 volts has got to rise up to 3 volts before we can switch it on again. The FETs themselves, if we want to look at the FETs, the pinout of the FETs is interesting. It has 4 pins that are the drain, and 3 pins which are the source, and a single pin which is the gate. So if we look at this, I can't work this out. I think that it's a mistake, but who knows. It says continuous drain current is 78 amps, and at 25 degrees C, at 100 degrees C, it's down to 49. But it also says here continuous drain current is what is it? Continuous drain current can be 20 amps and 18 amps. I assume this must be charging and this one discharging, but it does say that you can't expect more than 40 amps out of this because of the package style. So even if we've got our 20 amps, if it can give 20 amps, then that should be perfectly adequate, because the board's only supposed to be a 15 amp board. So if we look at this again and see how the FETs are connected, then yes, the drains connect together down the middle here. And for the discharge FET, then we have the 2 FETs connected, both gates connected together, coming down here from this resistor R5, what I've called R5 and R4. R4 comes from the pin on the chip, and R5 connects it to ground so that the FET isn't floating. And those 2 are for the discharge FET, and we have a similar layout here for the charge FET. So this island here has all the sources for the charge FETs connected together. And this island here has all the sources for the which way around is it? Discharge FETs connected together. So all in all, it's been an interesting sort of experience. I think I've covered everything there. We've done about the FETs, we've done about the circuit diagram, we've looked at the voltage, the graph, and seen that there is a discontinuity here. I'd really need something like a storage oscilloscope or something to be able to pick up which of the cells is actually misbehaving. But it's been an interesting example. Once again, please, if you're going to do anything like this, be very, very careful. Chances of fire and hazards are quite high. Make sure you've got a sand bucket or something nearby. Don't particularly want these things to go into water or get wet, I wouldn't have thought, if they catch fire. So a pair of tongs or heat-proof gloves, just in case things are gonna go wrong. Well, I've really enjoyed that. It's been an interesting look at this battery. But as I say, it does need great care. So it's bye now. Bye.